Okay. A system of equations is we're going to be solving simultaneously. What does that mean? If something happens, if things happen simultaneously, what does that mean?
You're writing and listening at the same time.
Yes. So they happen in at the same time,
Multitasking.
right? So we're going to solve. We're going to be solving two. You can solve as many as you want to, but we'll solve two equations simultaneously and see if they share any solutions. Now we're going to do linear equations because we know how to graph lines, right? We better. All right. So if two lines, if two lines have no solutions, that is an inconsistent, and I abbreviate here, system of equations. Okay. So if they share no solutions, that is an inconsistent system of equations. All right, draw that on your paper. Draw two lines that would share no solutions. All right, then these lines would be parallel to each other. All right, number two, a consistent system of equations has what it says here, at least one solution. Is at least. What does that mean? It could have one or it could have more than that, okay? So what if it just has exactly one solution? It is a consistent, independent set of equations or system of equations. All right, draw two lines that would have or share exactly one common solution. Draw two lines on your paper beside this that would have exactly one common solution. What are they doing? They're intersecting. If they intersect at a 90-degree angle, we would say that they're perpendicular. But really, they could intersect at any angle at all. Okay? So those would share a common solution. Finally, a consistent dependent system of equations has infinitely many solutions. Draw that. See what that would look like. How would you draw two lines that have infinitely many solutions? That one's probably the hardest one. What would they look like?
A circle?
They gotta be lines. They have to be lines.
I have many lines. What is
Two. What do you think?
Two lines on the same, like,
Yeah, look at him. Do it again. One's on top of the other, right? Like they are exactly the same line. And here's how I draw them. I just draw a double arrow so it looks like that.
Oh, man, that's what I
Good thinking. All right. So if they have infinitely many solutions, how many points are on a line? Infinitely many. And to have infinitely many common solutions, they would have to be the exact same line. Alright, so if we drew two lines, all the ways that they can relate to each other, what are the kind of lines we're going to draw? The first ones were parallel. The next ones were intersecting each other. And the last ones were the very same line, right? The very same line. Alright, so let's talk about something. Let's talk about their slopes. You're going to say either the word same or the word different. These two lines are parallel, so their slopes are
The same.
the same. We know that by definition of parallel lines. These lines intersect each other. They could be perpendicular or not, but they will. Their slopes will always be, say it, different. Their slopes will always be different. Like in this case, this one's positive and that one's negative, right? They don't have to be that way. But, if they're perpendicular, what do we know about their slopes? They are negative, what was that word? Reciprocals of each other. Alright, and then this line on top of that line being the same line, everything's the same. The slope's the same, the x-intercept's the same, the y-intercept's the same. Alright, so let's look at these. Let you copy this down, we'll talk about it. Good?
Yeah.
Alright, so this puts everything together. This would be a good thing to look at and study. An inconsistent system of equations. Graphically would be parallel lines. They have the same slope, they have no solutions. A consistent independent system of equations when you graph them, you get intersecting lines, whether they're perpendicular or they have some other slope, it doesn't matter. Their slopes are always different. That's the key thing to remember. And they have one ordered pair as a solution. Coinciding lines are what we call those lines that one on top of the other, they're the same line. So they have the same slope, the same x-intercept, the same y-intercept. And when you write this solution, you're gonna have to write it as a set. And I always put my simplest equation here because you have to write them as an infinite set of ordered pairs. Can't list infinitely many, so we have to do them as a set. And that is a consistent dependent system, okay? So this will have no solutions, this will have one ordered pairs of solution, and this will have an infinite set, and I'll show you how that works. Yes? So when you finish with your graph on these problems, you're not finished. You still have to name a solution, which will be this way, this way, or this way, and then you name the system, which will be one of these. I'll show you what I mean. Alright, let's look at this one first. On our first graph, let's write these two equations. And if you want to do two different colors with a colored pencil, that's fine. Or if you want to just, do it all with pencil, it doesn't matter. If you want to color code, I'm going to try to color code up here so that you'll know which, what goes with it. So I'm going to do this one in blue. Find its slope, its x-intercept, and its y-intercept. What form is this equation in?
No, standard.
It is in standard form, okay? And then I'll do this one in red. Have to find its slope, its x-intercept, and its y-intercept. Alright, what's the formula for finding slope?
Negative A over 2.
Good. So this would be negative 1 over 2. And the x-intercept is c over a, 1 over 1 is 1. And the y-intercept c over b, 1 over 2 is 1/2. We'll find the same three things with the second equation. A is 2, b is 1, c is 5. So negative a over b is negative 2 over 1. Alright, let's stop right there. I already know that these two lines will intersect each other. How do I know that?
The
Slopes are what?
slopes are
How did you
They're
get
not the same. They're different, aren't they? How did I get what now?
Negative on the slope.
Okay, negative a over b.
Oh, okay.
So negative 1 over 2 and negative 2 over 1. Alright, the x-intercept c over a, 2.5. The y-intercept c over b, 5. Alright, let's graph these two. The x-intercept is 1 on the first one. The y-intercept is 1/2, so go halfway up that box. I'm going to go back to the 1 and use the negative 1/2 slope. So if I go up 1, I go to the left 2. If I go down 1, I go to the right 2. And it's really important that when we graph our lines, that we go all the way across the coordinate plane, because we don't really know where these lines are going to intersect. So use your ruler and your point and stretch it all the way across there. Okay, my second line has an x-intercept of 2.5, a y-intercept of 5. I will go from the 5 up 2 into the left 1, or down 2 into the right 1. There it is right there. My point of intersection. Again, make our line stretch across the coordinate plane. And that is the graphing method, but what's our answer? The answer is going to be the point that they share. What is the only ordered pair point that they share?
3, negative 1.
Right, 3, negative 1. So that is our solution. By the graphing method, I know that 3, negative 1 is the solution that they both share, their common solution. And with intersecting lines, my system is consistent, independent. And this is our answer that we got using the graphing method.
So I did this right.
Did you get it?
I get it.
let's copy these two down. Okay, so our first equation here is in slope-intercept form, y equal mx plus b. So I have to find my information to graph it. And the second equation here, I have to do some work to that. Not quite in standard form. So if I multiply by the common denominator, so that I can get rid of the fractions, I would have 2x plus y equals negative 1. And that looks like it's going to be a little easier to deal with. There's no fractions. So I can find my three things that I need. From there. Now I think slope-intercept's easiest.
I like standard form.
Standard is pretty straightforward. If you know your formula, standard's easy, right? The slope, though, with the slope-intercept form is just given to us right there in front of x. The y-intercept is also given to us. It's b, which is 1. What is the formula for finding the x-intercept with slope-intercept?
Negative b.
That's right, negative b over b. So negative 1 over negative 3 is a positive 1/3. Alright, in standard form, here's A and B and C. So the slope is negative A over B. What can I already know? My slopes are different, so my lines will definitely intersect. Because if you look back at your table we wrote down, the only ones that have a different slope were the intersecting ones. Alright, and then C over A, negative 1/2. And then C over B, negative 1 over positive 1. And all we have to do is graph them like we have been doing for weeks, it seems like.
Is that negative 1/2 on the x-intercept?
It is right here.
On the slope, is it negative 2 over 1?
Negative 2 over 1. Yeah, I kind of squished that up too much. Alright, so here's my negative 1/2. Here's my negative 1. From negative 1, I would go down 2 into the right one. Up 2 into the left one. Remember to make sure your line goes all the way across the coordinate plane. And you can tell by looking at my line, it's got a negative slope because it's falling from left to right. Alright, and then here's this one with a 1/3.
Mine was just a tad bit off, like where they intersect.
Okay, that's the downfall of the graphing method. We're learning the graphing method first, but really substitution and elimination are no fail. And by tomorrow, y'all can tell me all the disadvantages to the graphing method after you look at your assignment. Alright, this is gonna negative 3, so up 3 into the left one, down 3 into the right one. The thing is, you have to make your lines perfect. And that's not always easy. Really important that you use a ruler. And a sharp pencil, that helps too. Alright, so what would you guys say the solution is?
2 negative 5.
And it is a consistent what? Independent or dependent? Remember, dependent one line's like
Independent.
holding the other up, so this one's independent. Sure. Go right ahead. Let's look at this example. Copy these down and then see if you can find the slope and both intercepts for each line. Try to graph once you think that we agree on all this information here. you should get, how do you know we're gonna get parallel lines? How do you know? Same slope. How do you know they're not coinciding? Everything's not the same, right? Alright, so I think I'm doing blue right now. So here's the X, here's the Y, here's a -1 slope. Up one to the left one, down one to the right one. And then 4 and 4 with the same slope. So where do my lines intersect each other?
They don't.
They don't. So what's my solution? Uh-oh.
There is none.
There is none. So what do we say when there is none?
Inconsistent.
Inconsistent, no solution, right? You're both right. So that is my answer. There is no solution. How do you symbolize that? Like this. And it is an inconsistent system.
That's the only problem.
That's a what?
Is remembering those things.
Yeah. Only 3 to learn though.
Yeah.
Alright, we still good with the graphing method? Alright, let me ask you a thinking question. When would the graphing method be not very useful?
When you have a graphic
In everyday life.
Actually, they're very useful.
when you have a graphic
System of
on the
equations.
equation.
Not if you're working at McDonald's.
Not if you're working at McDonald's, that might be true.
When you have a graphic.
Unless you own the McDonald's
Well, I don't.
and you want your profit to be more than your cost. Right? When would graphing method be not beneficial? You gotta tell me out loud. When would it not be beneficial? Any ideas?
When you have a graph and not an equation.
When you have what?
A graph and not an equation.
Well, if you already had the graph, that'd be cool. You'd have to, you could tell by looking.
Well, what if you had to find the equation?
Well, we do that some with word problems. Let me see if I can find some here.
Sounds exciting.
Alright, take this problem,
Parallel.
find the slope and the intercepts. How do you know it's parallel?
Because you can tell it has.
You can tell by looking at the slopes, right? Alright, find the slopes and the intercepts, graph, give the solution, and we'll do it for $1, okay? Alright, does anybody have a question? So far, you guys can look at a problem before you ever graph it and say those slopes are the same, but nothing else is, so they're going to be parallel. They're not going to have no solution. And then you can say, okay, those slopes are different, so they have to intersect somewhere. I just don't know where. So, graphing is the method that gets us there. All right, let's look at this example. Let's find everything we need to find on this one.
It's parallel.
All right, let's look. Be quiet now. Alright, so the slope, -2 over -2 reduces to 1. C over A reduces to 3. C over B reduces to -3. Up here, -A over B has a slope of 1. C over A is 3 and C over B is -3. Still think it's parallel? Everything's the same.
Oh,
So it's on top of each other?
Yeah, this is the same line twice. So I have an x-intercept of 3, a y-intercept of -3, a +1 slope. And the thing is, it's on both lines. So if you're doing it in color, I just do double arrows, just like that. That's not too hard, you just have to graph one line, cause they're the same. But now the solution set, remember, is a little more complicated. Alright, I have to list an infinite set. You can't write infinitely many of anything. So we have to write it in set notation. So it's the set of ordered pairs such that, or that fit into, does it make sense that if it fits into this equation, it fits into that one?
Yeah.
If it's a solution here, it's a solution there, and vice versa. Alright, you can write either one of these equations here. Which one would you call the reduced one? The
top
first one, yeah. Alright, I want you to notice something. If I took the first equation and multiplied it by 2, what would I get? The second equation. And that's one thing that you will notice, that one equation is a multiple of the other one. You'll notice that if they're both in standard form or slope-intercept form, you might not notice if one's in slope-intercept, one's in standard, or one is in totally no particular form at all. Alright, and then so I have to write my solution set this way, and I name my system. Does anybody remember what it is?
Consistent,
Oh,
dependent.
consistent.
Right. Right, y'all right, consistent, dependent.
Wait, so you have to make brackets on that?
Yeah, it's a whole set. Can't write infinitely many, so we have to word it as a set. Now that's all 3 types. We've found parallel lines that had no solution, inconsistent. We found intersecting lines that were consistent, independent. And this is the last example of consistent dependent system where there are infinitely many solutions. Alright, you guys do the whole thing on that. We'll do it for dollars. Record this. So, hang on a sec. Oh, wait.